Hello, everyone. Today, we're going to talk about applications of second law of thermodynamics. Last class, we worked on a second law of thermodynamics for pure substances. Today, we will continue the same application from the ideal gas point of view. Applications of the second law of thermodynamics for ideal gases. And first, we will start with an entropy changes in ideal gases. If we recall some equations of state for an ideal gas, we know that state equation for an ideal gas is that PV equals RT. And we also show that du equals Cv dt and dH equals Cp dt. What we're going to do in this lecture is that we are going to combine the state equations with the TS equations that we have driven in our previous lectures. So TDS equation with ideal gas equations. TDS, right? Our first TDS equation, TDS equals du plus PdV, and du, if I substitute my du, which is Cv dt plus PdV, divide both sides by T, ds will be equal to Cv dt over T plus P dV over T. Okay. And ds Cv dt over T, and if I use something else, instead of P over T, I can use R over V to satisfy the integration. All right. And combine second TDS equation with ideal gas equations. TDS equals dH minus VdP, right? If I substitute my dH here, Cp dt minus VdP, right? ds will be Cp dt over T minus V dP over T, or ds will be Cp dt over T minus R dP over P. So I have two entropy change equations from first and second TDS equations. Let's move on. So to determine to determine the entropy change for a finite change in state, we may integrate these equations. What were they? We just determined delta S equals CV dt over T plus R dV over V, and ds equals Cp dt over T minus R dP over P. We have two cases here, right? If I integrate entropy change for two different equations, right? I have Cv and Cp, which are constant or variable, specific heat constant. And I have two cases when I try to integrate the entropy change from one state to another. Right? I'm going to start with using the constant specific heat model. Constant specific heat model. Delta S from state 1 to state 2. dt over T from state 1 to state 2 plus R is a constant, I can take it outside of the integral, will be dV over V. Here, delta S entropy change from state 1 to state 2 at a constant specific heat model, Cv natural log of T2 over T1 plus R natural log of V2 over V1. Okay. Now using second entropy change, Cp integration from state 1 to state 2 dt over T minus R integration from state 1 to state 2 dP over P equals Cp natural log of T2 over T1 minus R natural log of P2 over P1. For an isentropic processes, we can pick any of these. I will start with the first one. Entropy change from state 1 to state 2 is Cv natural log of T2 over T1 plus R natural log of V2 over V1. So for an isentropic process, delta S equals 0, which gives me Cv natural log of T2 over T1 equals minus R natural log of V2 over V1, which leads natural log of T2 over T1 equals natural log of V1 over V2, the power of RC. Right? Or T2 over T1 equals V1 over V2, the power of RC. I know my R is the difference between Cp and Cv, right? And I also know specific heat ratio K is Cp over Cv. If I substitute these back in here, what I have is T1 V1, T2 V2, K minus 1. Okay. We just derived one equation for an isentropic process as a function of temperature and specific volume, which was T1 V1 to the power of K minus 1 equals T2 V2 to the power of K minus 1. So what if I need pressure, specific volume, or pressure and temperature? So what I can do is by using PVRT, right? You can try this by yourself. So for pressure specific volume, instead of a temperature, I'm going to write PV over R and times V1 to the power of K minus 1. After eliminating and organizing that equation, what I have for P1 V1 to the power of K equals P2 V2 power of K. Right? So if I want to get a temperature and pressure wise an equation from state 1 to state 2 for an isentropic process, instead of a specific volume, I can write R T1 over P1 to the power of K minus 1 times T1 and T2 times R T2 over P2 inside the parentheses to the power of K minus 1. I will end up with T1 P1 1 minus K over K equals T2 P2 to the power of 1 minus K over K. Okay. So I have 1, 2, 3. Process lines for ideal gases. Pressure versus volume and temperature entropy diagram. Entropy, temperature. So what I'm going to visualize here, sketch on a PV and TS diagram, is PV to the power of n equals constant. This represents pretty much all the process lines that I need to know for an ideal gas. Okay, for example, if n equals 0, right, P equals constant, right, which makes the process line isobaric. Right? If n equals 0, the process is isobaric. Right? If n equals infinity, process is isometric. Right? N equals infinity. N equals 1, PV equals constant, process becomes isothermal. So isothermal process, N equals 1. And N equals K, the process becomes isentropic, which is a steeper curve. Right? N equals K. And on the TS diagram, N equals 1, isothermal, N equals 1. N equals K, entropic, N equals K. N equals infinity, N equals infinity. And N equals 0. N equals 0. And when N equals 1, the process line is isothermal. when n equals 0, it's isobaric. When n equals k, it's isentropic. When n equals infinity, it's isometric. All right. Example. For an air is an ideal gas. Air is an ideal gas with constant Cp equals 0.241 BTU count degree Rankine, is compressed from a state where the pressure is 15 psi and the temperature is 80 degrees Fahrenheit, to a state where the pressure is 50 psi and the temperature is 240 degrees Fahrenheit. Can this process occur adiabatically? We need to figure this out. If yes, determine the work in BTU per pound. If no, determine the direction of the heat transfer. Last but not least, sketch the process line on a TS that we have a system which contains air, it's an ideal gas, right? And air inside system is compressed air with a Cp equals 0.241 BTU per pound degree Rankine. Right? And system goes from state 1 to state 2, where pressure on is 15 psi and temperature is 80 Fahrenheit, to state where pressure is 50 psi and temperature is 240 degrees Fahrenheit. Right? What condition must be true for this process to occur adiabatically? Right? I know from previous lectures that delta S, entropy change from state 1 to state 2, should be higher or equal to 0 at best. So delta S, entropy change for this problem from state 1 to state 2, delta S, Cp, natural log of T2 over T1, minus R, natural log of P2 over P1. Right? Delta S Cp is given in the problem 0.241 BTU per pound degree Rankine, natural log of temperature ratio 700 degree Rankine over 540 degree Rankine. Okay, these are absolute temperatures. And R is a universal gas constant over a molecular weight. 1.98 BTU per pound mole degree Rankine over molecular weight of air is 28.97 pound per pound mole, right, times natural log of pressure at state 2 over pressure at state 1. From here, delta S, entropy difference from state 1 to state 2, delta S will be equal to minus 0.0197 BTU pound degree Rankine. Since entropy difference is negative, this process cannot occur adiabatically. Right? Remember, we have to satisfy this condition to check if the process is adiabatic, which doesn't satisfy this condition. So this process cannot occur adiabatically. So there must be a heat transfer out of the system, because I know the temperature is an absolute temperature, cannot be negative. The only way this term to be negative is heat transfer occurring outside of the system. Okay. So heat transfer out of the system. You're also asked to sketch this on a TS diagram. Entropy, temperature, at state 1 and state 2. It is an irreversible process occurring from state 1 to state 2. Right? Temperature rises, entropy decreases, which puts me in this on a TS diagram. Okay, so let's continue on entropy change. Entropy change and ideal gases. But in this case, we are going to look at from variable specific heat model. Using variable specific heat model, right? Entropy change into states from 1 to 2, Cp dT over T minus R dP over P. Statement 2 equals. In the first case, where my specific heat was a constant, I took it outside because it was a constant. Now I cannot take it outside. Right? So here, instead of solving this integration, there's a new parameter that I can extract from a table, which is S0 minus S20 minus S10 from state 1 to state 2, right? So someone solve this integrations as a function of temperature for the variable specific heat model and tabulate it for us, and we go and read it from the ideal gas table. Please be careful that these S values are not entropy. These are a product of entropy, okay? And this term is same, R, I can easily integrate this term, minus R natural log of P 2 over P1. Okay. And again, where this F0 is a function of temperature and it can be found on an ideal gas tables. Isentropic process. Isentropic. An isentropic process, right? Delta S from state 1 to state 2. S2, 0 minus S1, 0 minus R natural log of P2 over P1, right? For an isentropic process, it's 0. So natural log of P2 over P1 equals S2, 0 minus S1, 0 over R. P2 over P1 will be equal to exponential of S2, 0 over R over exponential of X1, 0 over R. Okay. Let this term exponential S0 over R as our reference pressure. Okay. If I use this expression and substitute back into my pressure ratio P2 over P1 for an isentropic process will be PR2 over PR1. Okay. So what I had, pressure, state 1 to state 2 is P2 over P1 equals PR2 over PR1 relative pressure. And let use our state equation PV equals RT, okay, or T2 over V2 divided by R T1 over V1 will be equal to PR2 over PR1, right? If I leave my specific volume alone, so V2 over V1 equals T2 divided by PR2 over P1 over PR1. I call this P over PR ratio as VR. If I do that, this V2 over V1 will be equal to VR2 over VR1. Specific relative volume for state 1 and state 2. Okay. Example. A quantity of air undergoes a thermodynamic cycle consisting of three internally reversible processes in series. Process 1 to 2 is an isothermal compression from pressure 1 1 bar, 2, pressure 2 was 4.751. Okay. Process 2 to 3, the constant pressure expansion to temperature 390 Kelvin. And process 3 to 1 is adiabatic expansion to initial state. By employing ideal gas model with variable specific heats, A, sketch the cycle on PV and TS diagrams. B, is the cycle a power cycle or refrigeration cycle? C, if a power cycle, determine thermal efficiency. If a refrigeration cycle, determine coefficient of performance. Okay. Okay. Let's start with sketching PV and TS diagram. But before it ends, I would like to give you a table where I can show all my variables and properties, if you will. With 4 columns and 9 rows. First column is where the state, okay, state 1, 2, 3. The first column is for our properties: pressure, temperature, specific volume, meter per kilogram, enthalpy, internal energy, entropy product as 0, PR and VR. Right? Kilojoules per kilogram entropy, internal energy is kilojoules per kilogram, S0 kilojoules per kilogram, B Kelvin. Okay? In the problem statement, I'm given the first pressure, which is 1 bar. Okay? 1 bar. At state 2, pressure is 4.75 and state 3 is 4.75, because I know that process from state 2 to state 3 is constant pressure. Okay? And I'm also given the temperature at state 3. Okay. This is all I know about the problem. Okay. Let's move on to our PV and TS diagram. Entropy, temperature, right? From state 1 to state 2, process is isothermal, State 2 to state 3 is isobaric, and state 2 to state 3 to state 1 is adiabatic. Okay? State 1, state 2, state 3. TS diagram, state 1 to state 2 is isothermal, state 2 to state 3, isobaric, and state 3 to state 1 is isentropic. 1, 2, 3. Oh. Let's start finding my properties for the table for problem to calculate my work, heat, stored energy in the system, entropy generation, etc. Okay? So when I look at the table, I can tell that the starting from the state 3 is more reasonable because I know more properties. Okay? So let's start from state 3 by solving for specific volume at state 3. Right? Specific volume at state 3 equals R P3 over P3 equals, I know my R 0.287 kilojoules per kilogram Kelvin times temperature is 390 Kelvin over pressure is 475 kilopascal. Right? From here, specific volume can be found as 0.2348 meter cubed per kilogram. Okay. Specific volume 0.2348 meter cubed per kilogram. I can also write my other properties because I know my temperature. If I go to ideal gas table, I can also extract them from the table. Enthalpy will be 390.88. Internal energy will be 278.93. Entropy, product of entropy at 0 will be 1.96633. PR 3.481, and we are 321.5. Okay. Okay. So I know, let's put this on the side. The process from state 3 to state 1 is adiabatic, right? Adiabatic means that this process from state 3 to state 1 delta S is 0, right? So P3 over P1 equals PR3 over PR1, right? So PR1, I know my P3, I know my P1, I also know my PR3, so I can calculate my PR1. PR1 here will be 3.481 times 1 bar over 4.75 bar. So PR1 0.7329. So I know one more property at state 1 now, which is relative pressure. Right? If I go back and substitute this back into my table, 0.7329, right? And at 1 bar and PR, if you go to an air table, an ideal gas, PR value should be at temperature 250 Kelvin, right? So by knowing one of your value, one of your property at a specific state, you can check your temperature, right? And knowing your temperature gives you other properties. Right? Enthalpy is 250.05. Right? Internal energy 178.28. S0 is 1.51917, and VR is 979. Okay. Okay. But we need to calculate our specific volume at state 1. VR equals R T1 over P1. R is for air, R is 0.287 kilojoules per kilogram Kelvin times 250 Kelvin over P1 is 100 kilopascal. And V1 equals 0.715 meter cube per kilogram. And specific volume is 0.715 meter cube per kilogram. Huh? Okay. Since process 1 to 2 is isothermal, given in the problem, all air table properties can be copied from state 1 to state 2 because temperature is same, right? 250. Enthalpy is 250.05. Internal energy 178.28. S0 is 1.51917. VR is 0.7329. And VR is 979. But I need to calculate my specific volume at state 2. Okay. So at specific volume at state R T2 over P2 right? 0.287 kilojoules per kilogram per Kelvin times 250, right? Or 475 kilopascal, which gives us 0.05, right? 0.1505 meter cubed per kilogram. Right. Now I can go back and put this on my head. 0.1505. Okay. Okay. So I completed my table. Now I have everything I need to complete this graph. Okay. All right. Let's start from first process. Process 1 to 2, right? It's an isothermal process. Isothermal, where temperature difference is 0, right? Which means delta U is 0. Okay? So, on first law of thermodynamics, Q minus work from state 1 to state 2 equals internal energy difference between the states. If U is different, if U is same between two states, Q1 to 2, right, equals work from state 1 to 2. And I know how to find my work. Work from state 1 to 2 is P dV from state 1 to 2. And P R T over V, right, dV from state 1 to state 2 here. So this is R T over V. R is constant. I can take it outside. And temperature from 1 to 2, temperature difference. And natural log of V from state 2 over state 1. Right? In this case, I can also take temperature outside because it's a constant. Right? All right. So work from state 1 to state 2, work from state 1 to state 2 will be 0.287 kilojoules per kilogram degree Kelvin times 250 Kelvin. Natural log of specific volume at state 2, 0.1505 over specific volume at state 1 is 0.715. Here, right, work from state 1 to state 2 will be minus 111.41 kilojoules per kilogram. And that way, I can find my heat from state 1 to state 2, which is equals to work from state 1 to state 2, 111.41 kilojoules per kilogram, right? This tells me that Q is out, right? Okay. So process from state 2 to state 3, right? Isobaric, where delta P equals 0. Okay. Energy equation for thermodynamics from state 1 to state 2. Q from state 2 to state 3 minus work from state 2 to state 3 equals internal energy or stored energy inside the system from state 1 to state 2 to state 3. And heat transfer from state 2 to state 2 will be equal to internal energy difference from state 1 to state 3 plus work interaction in the system from state 2 to state 3. Okay? Then I can calculate my work from state 2 to state 3 PdV equals pressure from state 2 to state 3, right? Which is equal, I can take it outside, and specific volume difference from state 3 to state 2. All right. Work from state 2 to state 3. Pressure is 4.75 bar, right? Times specific volume difference. Specific volume at state 3 is 0.2348 meter cube per kilogram minus 0.1505 meter cube per kilogram. This is bar. I need a unit conversion, 100 kilopascal over 1 bar. Pascal, bar goes away, meter cube per kilogram, kilojoules per kilogram. All right. So from state 2 to state 3, work is 40.04 kilojoules per kilogram. Okay. So heat transfer from state 2 to state 3 equal 40.04 kilojoules per kilogram, which is work, and plus internal energy difference, right? From state 2 to state 3, U2, U3 minus U2, U3 was 278.92 minus 178.28 kilojoules per kilogram. Heat from state 2 to state 3 was 140.69 kilojoules per kilogram, which is Q. Okay. Last process from 3 to 1, which is adiabatic. Adiabatic, where Q is 0. Right. Q from state 3 to state 1, we come back out initial position. Work from 3 to 1 equals internal energy difference from state 3 to state 1. Right? Heat is 0. So heat work from state 3 to state 1 will be equal to delta U minus delta U from state 3 to state 1. Work from state 1 to state 3 equals minus U3 is 178. Sorry, U1 equals 178.28 minus 278.97 kilojoules per kilogram, right? U1 minus U3. The work from state 1 to state 3 to state 1 equals 100.69 kilojoules per kilogram, right? When the heat interaction from state 3 to state 1 equals 0. Okay. Cycle. So if we go back to our diagrams, right? I need to determine, now I have everything. Before going forward, I need to determine my